Welcome to the gas law review. And before we get started on the actual review, let's talk about what you're going to be given on the test. And you will be given the combined gas law, and you will also be given the ideal gas law along with the ideal gas law constant. Remember, we talked about in class, if you're dealing with the combined gas law, that you can actually get Charles's, Boyle's, and Gay-Lussac's out of that by holding one of the parameters constant. For instance, if I was to hold temperature constant, meaning it's the same on both sides, I would be left with Boyle's law. And then if I was to hold pressure constant, so I take out these two pressures, I'm left with B1 over T1 equals B2 over T2, so that would be Charles's law. And then if I was to hold volume constant, take out volume, I'm left with Gay-Lussac's law. So you should be able to use that law to solve any of the gas laws. And then, of course, there's the ideal gas law, and that is when, remember, we use that whenever we don't have two parameters changing. For instance, we only have one pressure, one temperature, one volume, then we would solve for moles. But the combined up here, we would use that like if there's, a pressure and a volume, and they change the pressure and they want to know the new volume, that's when you would use the combined gas law. Okay, next slide, we'll talk about what you don't get. So these are the things that you're going to have to memorize for the test. You need to know your pressure conversions. Remember, 1 atmosphere is equal to 760 millimeters of mercury, or torr, they're the same thing, which is equal to 101.325 kilopascals. You for sure need to know how to convert your temperature to Kelvin. It's the easiest conversion we have. Your Celsius plus 273. And remember, that is for every single temperature, every single time. No exceptions. Always have to have your temperature converted to Kelvin. And then, of course, you need to know what STP conditions are. And that was 1 atmosphere and 0 degrees Celsius, which is the equivalent of 273. Sometimes that trips kids up because it says the gas was held at STP, and they're like looking at the problem going, but I don't know how much it is. I don't know what the conditions are. And so whenever you see STP, you need to remember that it's a standard pressure of 1 atmosphere, and temperature is 0 degrees Celsius or 273 K. All right, these next two slides are going to be talking about the terms that you need to know listed at the top of your review. First of them is the ideal gas law constant, which you will be given. But what you need to remember about the ideal gas law constant is when we use that, your units that you're putting in the ideal gas law have to match these units here. So that means your volume's got to be in liters, your pressure's got to be in atmosphere, and amount has to be in moles, and then temperature, of course, is in Kelvin. You need to know what Boyle's law is in terms of how to solve for it. Pressure and volume inversely proportional. You for sure need to know that. It helps because those are the only two conditions that are inversely proportional with each other. Everything else is going to be directly. And so that kind of helps you remember that. Dalton's law of partial pressure. That is a law that states that the total pressure is equal to the sum of the partial pressures. We used this law when we did our molar volume of a gas because we had to account for the vapor pressure of the water that was also collected along with the gas. And so we used that law as well. And then, of course, the last one is the ideal gas law, or PIV-NERT as we like to call it. And again, I just want to reiterate that when you use that R value right here for the ideal gas law, that means that all of your other units have to match the units that are in the ideal gas law constant so that we can get them to cancel out. The rest of these are combined gas law, which you will be given on the test. Charles's law is the one that relates volume and temperature. And remember, they are directly proportional. If I increase the temperature, I increase the volume, or vice versa. If I decrease the temperature, I would also decrease the volume. You need to know the definition of effusion, which is the ability of a gas to pass through a tiny opening. Remember, we said a flat tire was an example. Remember, diffusion is the other one. Diffusion is where the gas particles spread throughout the room or a container and equally mixed. That's why we can smell perfume when it's being sprayed, or that's how air fresheners work. And then lastly, the last definition that we need to be aware of is the Gay-Lussac's law, which is the law that relates pressure and temperature. And of course, they are also directly proportional. Meaning if I increase the temperature, I increase the pressure. We use the example in class of the aerosol can, which remember I told you is very dangerous, don't do it, but that is why it explodes when you put it in a fire, because the temperature begins to heat up. The particles inside move faster, and so they're hitting the sides of the container more frequently and with more force, ultimately increasing the pressure to the point where it can't contain it and it bursts. So those are the definitions we needed to know. So let's get started on some of the rest of the review. All right, as the pressure of a gas at a fixed temperature increases, the volume will, and so we're relating pressure and volume. And so if the pressure is increasing, then the volume will decrease. So this is going to be decrease. We're going to abbreviate that. Next one wants to know, as the temperature of a gas at a fixed volume. When it says fixed volume, we don't need to worry about it. Same thing up here, fixed temperature. It means it's not going to be a factor. It says as the temperature is increasing, the pressure will do what? Well, like we just said, the pressure and temperature are directly proportional, so it would also increase. And then number 3, the volume of a gas at a fixed temperature means we're going to ignore it. The volume of a gas at a fixed temperature increases. What's going to happen to the pressure? And they are indirectly proportional or inversely. So if the volume is increasing, then the pressure is going to decrease. So we would need to put decrease here. And then it says if you know the mass and volume of a gas at STP, you can also calculate the molar mass. And we used a special equation for that. And so I'm going to give that to you, but if you want to use this equation and not do it the hard way, you will have to memorize this. And that was the dirt over P equation that we used, the molar mass. Remember we said it was the kitty cat equation. Kitty cat goes meow, goes to the bathroom, and then puts its dirt over its P. And then, of course, we said density is D, and that was grams per liter. So that is why if you know mass and volume, because that's what this is, mass and volume, you could figure out the molar mass of a gas. Number 5, under what conditions do real gases most resemble ideal gases? In class when we discussed this, we said the times that they would behave most ideally is when they are far apart. The particles are far apart from each other. And so the 2 conditions that we have there are low pressure, because when the pressure is low, the particles are not being pushed close together. And one of the other conditions is high temperature is the next one, and that's because when the temperature is high, the particles are moving faster and able to move further away from each other. And then the final condition that can sometimes affect it is nonpolar molecules. And remember, nonpolar molecules have equal sharing of the electrons, and so there's no slightly positive or slightly negative in, so the particles are not attracted to each other. Number 6 and 7 are pressure conversions. And so let's talk about what the pressure conversion is. And then I want you to pause your video, you work the pressure conversion, and see if you get the correct answer. All right, here are the answers to those 2 problems, and hopefully you got that correct. The reason we did 2 significant figures, just to kind of clarify, is because this has 2 significant figures, and so does this one. Because there's not a decimal right there, that only has 2 significant figures. So let's move on to the next one. Number 8, if the pressure of a sample of argon is 3.4 atmosphere in a 400 milliliter container, and the container is compressed to 50 milliliters, what is the new pressure? And so we're dealing with pressure and volume in this particular equation. And so we're going to use this using the combined gas law, and then we're going to take out what we don't need in the combined gas law. So remember, the combined gas law is P1V1 over T1 is equal to P2V2 over T2. And of course, we are not dealing with temperature in this particular equation, so we can cross out temperature, and then we see that we're left with Boyle's law. And so let's just identify the parameters, and then I want you to pause the video and work the problem yourself. So it says we have a pressure of 3.4, so that's going to be P1. We have a volume of 400 milliliters, so that's V1. And we see that the container is being compressed to a volume of 50 milliliters. So that's going to be V2. And it wants to know what is the new pressure. So pause the video and calculate and see what you get. So how'd you do? Hopefully you got 30 atmosphere. The calculator probably gave you 27.2, but because we need one significant figure, oops, I said 2, and it's actually 1, sorry about that. One significant figure, because this has 1 and this has 1, so our answer is 30 atmospheres. And then we can double check ourselves and say, hey, we know that the volume decreased, and because they're inversely proportional, we would expect that the pressure would increase, and it did, so we are on the right track. Number 9, at 8.9 degrees Celsius, the volume of a gas is 56 milliliters. At the same pressure, the volume is 89 milliliters at what temperature? So I see that we will not be using pressure because it says same pressure. So when I go to use that combined gas law, which is, hopefully by now you have written this enough that you recognize it, but when I write that combined gas law, I know that I'm going to be able to leave out pressure, so I can mark that out, and I'm left with Charles's law. And so now let's identify our parameters. We have T1 right here, and V1 right here, and we are going to change the volume to V2, and it wants to know what the new temperature is. Okay, so let's go ahead and cross multiply this particular equation. So we'll have V1 T2 is equal to V2 T1, and now pause your video and work that calculation out. Remember to change your temperature, T1, to Kelvin. All right, we should have gotten 450 Kelvin. Your calculator probably came out 448.02, but because we need two significant figures, our answer is 450 Kelvin. And let's do our double check. We saw that the volume increased, and so we should expect our temperature to increase, which it did, and so we are on the right track. Number 10, the volume of a gas is 560 milliliters at 45 degrees Celsius. If the temperature is increased to 67 without changing the pressure, what is the new volume? And so I want you to try this one completely on your own, labeling it, figuring out what formula you need to use and all that stuff, and then come back and check and see if you have the right answer. So hit pause. All right, so we should have been using Charles's law in this one once we cancel out the pressures. And so we're going to be solving for volume 2. And so when I rearrange that equation for volume 2, I'm left with this, V1 T2 over T1. And so after I've converted my Kelvin temperatures, I plug those in, and I get an answer on the calculator of 598.742. If I go back and look at my parameters, I see that I need two significant figures. This has 2, and so that's going to limit our amount. And so the only way I can get that particular number into two significant figures is to put it in scientific notation and write it as 6.0 times 10 to the second milliliters. All right, how are we doing so far? All right, let's keep trucking. Here's another one, number 11, that I want you to try completely on your own. And so pause the video and work out whatever formula you need to do, whatever temperature conversions, and let's come back together and see if you get the correct answer. All right, hopefully you got 1.7 atmosphere using the correct number of significant figures. And as you look over this problem, you should have noticed that there was no volume involved. And so if we take that combined gas law and take out the volume, we're left with Charles's law. And then we rearranged Charles's law to solve for P2, and then plugged everything in, and hopefully you got 1.7 atmosphere. If you did not get that answer or any of the previous answers, you need to go ahead and pause the video and maybe get out a sheet of paper and try to rework the problem, but not looking at the work that's on the screen or on your homework that you've already done. All right, so let's move on to only 2 more problems left. Okay, I lied. It's actually 3 problems left, not 2, but let's get going on them. Number 12 says 4 samples of gas each exert a pressure of 800 torr of pressure in a separate 3-liter containers. What is the pressure if they are combined into one 3-liter container? So this is simply that Dalton's law where we do P total is equal to however many gases we have, which in this case is 4. So it's going to be P1 plus P2 plus P3 plus P4. Okay? And if we read the problem, it's 800 torr for each. So go ahead and pause and do that math real quickly. So hopefully that was really easy for you. We had 4 samples of gas, each exerting 800 torr of pressure. So all we did was add up 4 gases, 800 each, so we should get 3,200 torr. Number 13, what is the volume of 3 moles of oxygen at STP? And remember when I told you when we see this STP, that doesn't mean that we don't have the conditions. It means it's given it to us in this shorthand form. And so, of course, standard temperature is going to be 273 Kelvin. And then we said standard pressure was 1 atmosphere. Okay? And so if you can read the problem again, you're getting a pressure, you're getting an atmosphere of pressure, you're getting a temperature of 273 K, and you're getting an amount in the form of 3 moles. What you're not getting is volume. But because we don't have any parameters that are changing, that is our clue that we're going to use this PV equals nRT. And remember R, we're going to be using 0.0821 liters times atmosphere over mole K. So luckily in this problem, it doesn't look like we need to do any converting. So pause it and plug these things into the ideal gas law and see if you get the correct answer. All right, I hope that you got 67 liters like I did. If you didn't, pause the video and see what you did incorrectly, or, make sure I haven't made a mistake. I'm pretty sure I haven't, but, I sometimes make mistakes as well. But let's take a second real quick to look how these units cancel out. We have a mole on the top and a mole on the bottom, so they cancel out. We have a Kelvin on the bottom, a Kelvin on the top, so they cancel out. And we have an atmosphere on the top and an atmosphere on the bottom. So that leaves us with our unit of liter, which is good because we are solving for volume. All right, now one last problem. Let's get to it. A 3.2 liter sample of gas with a mass of 3.45 is collected at 34 degrees Celsius and 765 millimeters of mercury. What is the molar mass of the gas? So we are going to be using that dirt over P formula that we've talked about. So we're going to need to solve for a density. So remember we said density is mass over volume, in this case grams per liter. So I'm going to take the 345 grams, 3.45 grams, and I'm going to divide it by the volume of 3.2 liters. And that is going to give me a density, and then I'm going to plug that into this equation right here. So I want you to do that right now. So pause it and let's meet back in a second. So the answer with the correct number of significant figures is 27 grams per mole. If you did not get that answer, a couple of things I want you to make sure you noticed is that you had to convert this pressure from millimeters of mercury to atmosphere. So if you didn't do that, that's going to give you a very incorrect answer. And then of course when you divided your density problem over here, you should have gotten 1.08, and of course that's what you plugged in right here for density. And then we have our R value, and then of course the temperature, which we always convert to Kelvin, and then our pressure conversion. So most likely if you didn't get it correct, most likely you forgot to convert that pressure. So when we're reading these problems, we have to be very careful. Anytime we're using that R value, remember your units have to match, which means your pressure also has to be in atmosphere. All right, only one joke this time, and the joke is, why did the gas molecules peak in the window at night? They were PIV-nerded. All right, I hope this gas law review helped. Good luck on your test. See you in class.